Today we're going to talk about something different from discrete classification. We're going to be talking about working on continuous data and using techniques called regression analysis. So in the discrete case, we only had a limited number of choices of outputs. Our y's were plus or minus 1 or from a very small set. But now we're going to talk about y's that can be anything. They can be any real valued number. And our input x's can also be any real valued number, and we want to, as usual, predict y's from our x's. And in this case, each data point is an observation. Again, it's an xi and a yi, but now they're both real numbers. And the kind of analysis tool that does this for this one-dimensional case is a line mapping your x's to your y's, and we call this a regression line. So some examples of regressions that you might want to do, given a child's age and gender, what would their height be, given unemployment, inflation, and number of wars, on and on and on, what might the president's approval rating be? Given a browsing history, how long will a user stay on a page? These are all places where the output is some real number, not a single output, but something that makes sense to double, for instance. So any questions on the setup?
Nope.
Okay. Just to recapitulate this a little bit, our data points are xi, yi, and we have some beta vector that we multiplied by our data to get our prediction, and this is our prediction of the y. Any questions?
No.
Okay, all right. Yeah, so fairly straightforward. This looks a lot like logistic regression that we talked about before. The only difference is that we're not wrapping our predictions in a sigmoid function. So this should look very familiar to you. And just like logistic regression, we have our data as a vector xj, and we have a bias term. This is also called an intercept. When we have a vector, this just becomes a sum. Okay, so this is what it looks like when you turn it into a vector. You have a high number of dimensions, and now instead of a line, we have a plane as our prediction function, given x1 and x2. You can do things like feature engineering on regression, just like you can for discrete classification. You can transform your data, take the log of it. You can multiply things by themselves. You can have indicators that just say, does a value fall within a range? You can have interactions. So you can do lots and lots of stuff with the inputs to create new ways of encoding your data. And because of its simplicity and flexibility, this is one of the most widely implemented ways of analyzing continuous data. Okay, so let's talk about fitting a regression. So we've been talking about classification techniques that have objective functions. The objective function for linear regression is what's called the residual sum of squares. So the residual comes from looking at the distance between your prediction and the truth. Squared, because you square it. You want to penalize things that are further away rather than things that are close. And sum because of the sum here over all of your data points. And so you can use calculus to figure out that the value of your coefficient that minimizes the residual sum of squares is this. We'll see the linear algebra form of this in a second, but this is relatively straightforward to compute when your data set is of a reasonable size. And if you want to make a prediction, you take this function, and here's the function written as a line. If you want to predict for a point like 0.5, or sorry, 5.0, you find that place on this axis, you go up and see where it hits the line. In this case, it's 3.5. Okay, so this has all been fairly straightforward, so thank you for your patience. Now let's make this a little bit more than you might have seen in, say, a high school class. We haven't talked about a probabilistic interpretation. We use probabilities a lot in this class. So what's the probabilistic interpretation of linear regression? So what happens is that you can think about each prediction coming from a Gaussian distribution, where the mean of that Gaussian distribution is your input vector times the weight vector. That becomes the mean of a Gaussian distribution with some variance. And so you can think about that as having a Gaussian curve at every point. Where the center of the Gaussian curve is depends on where you are on the line. And so this should make sense in the residual sum of squares sense, because the density function of a Gaussian looks something like x minus the mean squared. Or it's proportional to that, at least. Okay, any questions on that interpretation?
No.
Okay, and if you minimize the residual sum of squares, then that's equivalent to maximizing the conditional likelihood. And so this should remind you a lot of logistic regression, where we're maximizing the probability of y given x for all of our data points, and we have the product over all of those. And so instead of having a logistic function, we now have a Gaussian function. Mm-hmm. Okay, so let's look at some examples. So let's say the guys are Old Faithful. So this is a something in Yellowstone National Park. It erupts every some number of minutes. It's fairly regular, but it has a little bit of variance. And we can try to model that using regression. So this is what the data look like. So this is how long you have to wait until the next eruption, and this is how long the last eruption lasted. And so if you have a long eruption, you have to wait more. I guess it tired itself out. So we can fit this using tools like R, or you can use sklearn, whatever you want. But you get out the intercept term, beta naught. You get the linearity coefficient here. And then we can make predictions for various points if we want to. And out come the answers. So that's what the line looks like.
The answers were the y value for the x's that you were trying to predict
yes.
on? Okay.
Yep. And so if we plug into, if the current eruption lasted 2 minutes, then it says that we have to wait about an hour, a little less than an hour. Okay, so any questions on that example?
No.
All right. So now let's talk about multivariate linear regression. If you have 2 points, you can fit that perfectly with a line. That's a fact from geometry. And so the line is close to all points when you have exactly the right number of observations given your dimensionality. But let's think about what happens when we have very high dimensional data. And to talk about that, we need to add some new vocabulary terms. And so there's bias, variance, and noise. And each of these can cause our model to go wrong. So bias is error that we have that is introduced because we chose the wrong model. Variance is when our input data is noisy and we choose the wrong data because we thought that there was signal in the noise when there actually wasn't. And the noise is just inherent difficulty of the problem. And so as our model becomes more complex, we're prone to variance. And so we talked about this in our theoretical analysis of machine learning algorithms. As our Rademacher complexity went up, our generalization ability went down, our error went up. And the bias is basically how we go wrong from choosing the wrong model. And so we might have said that we believe that one coefficient is 0 when it actually isn't. That can cause error. Bias can be very bad when you have very low model complexity, when you're making very strong assumptions and you have very few models to choose from. But as we can see that as your model becomes more complex, bias can help you not to get too led astray by variance. And so let's see why that might be. And so in linear regression, if you have a lot of covariates, a very high dimensionality, and very few observations, you can be led astray. And you can't use linear regression because it depends on having a good number of observations for every dimension. And what we can do is, to counter this, is to introduce some bias. That we want to say that if we have a large number of dimensions or covariates compared to our observations, then most coefficients should probably be 0. We don't have enough information to say anything about it. And so we should set most of them to be near 0. And this may not be a bad assumption, because if you have thousands of dimensions, thousands of coefficients, can they all be equally important? And can you actually learn that from the data? Okay, so any questions on the setup? Okay, so for example, let's take a look at microarray expression data. And so we're trying to predict whether someone will have some condition and in the future. And we have their genetic data. And this is very high dimensionality, tens of thousands of genes, and only hundreds of patients. And so the dimensionality is really, really high, but we don't have that many observations because it's expensive to get these data. What does bias mean in this case? If we introduce bias, this is basically saying that most genes are not going to be relevant for any particular condition. Most genes are going to encode completely irrelevant information. We're looking for ones that do encode something worthwhile.
They're called housekeeping genes.
Okay. All right, great. Yeah.
Ones that just kind of keep things normal. And it's
Yeah,
the ones
and
that go way up or down that.
Exactly, and you could have things that go way up or down but are just completely irrelevant and don't predict lymphoma. Mm-hmm. It could be related to whether you like having your genes sequenced, and that's irrelevant for predicting lymphoma. And okay, so this is a regression problem. The inputs are continuous values, and the outputs, like how long will it take before you get lymphoma, is also a continuous value. And the inputs are from microarray data. How does this gene respond in a particular situation? So does it matter which gene we select for prediction? Some people may argue yes, but if we're only caring about prediction, it doesn't really matter. We just want to know, is this person going to be alive in 3 months or not? And if you are only focusing on a smaller number of coefficients, rather than tens of thousands, you're going to be less susceptible to noise. Okay, so that's the intuition. We want to focus on a small subset of the genes. How do we do that mathematically? And so we're going to do something similar to what we did for logistic regression. We're going to use a technique called regularization. And so we're still going to mostly optimize residual sum of squares. But we're going to place a penalty on cases where the betas are big. So does that make sense?
Right, because we don't want any one beta to get too out of control.
Exactly. And so we still have this residual sum of squares in our objective function. This is what we're trying to minimize. And we're going to add in this penalty term that is related to how big they are. And we're going to have a term lambda, like we did for logistic regression, that basically says how important is this versus everything else. So there are two main kinds of regularization that are talked about in the literature. If you take your betas and square them, this is called ridge regression. If you just take the absolute value, this is called the lasso. So any questions on this? We'll compare them in a second.
Okay.
But the component of fitting your data is still exactly the same. All right, so let's compare the ridge and the lasso. The objective is squared for the ridge, absolute value for the lasso. Ridge has a closed form estimator. So this is a linear algebra equation. You can write it down and get your betas out nice and easy. It's more difficult for the lasso, but we'll talk about that in a second. For ridge regression, most of your coefficients will be close to 0. But not exactly 0. That happens in the lasso because of this term. So this penalty looks like this, and so you can always make it smaller and smaller and smaller and get extra reward. Whereas for ridge regression, it looks like this, and so as you get closer and closer to 0, you get diminishing return for making it smaller. And so lasso is what you want if you want to know exactly which genes are on, which genes are off. And this is often called an interpretable estimator, one that you can read. So that's a plus for lasso, but one downside of lasso is because of this, very small changes in x or y causes the set of active inputs to be dramatically different, whereas ridge is a little more stable. If you change x or y a little bit, the betas won't change too much, but with lasso, it can radically change. Okay, so any questions on comparing ridge and lasso?
No.
Okay. They both have this tunable parameter lambda, and typically you want to use cross-validation to find the best lambda. So try out a bunch of things on development data, see what works best. Okay, so to wrap up, we talked about regression. It's a workhorse of data analysis. It's part of fundamental tools, some of which we've seen before, like the logistic regression. Hopefully we have enough intuition now to understand the interpretation of the regression parameters, because we'll be using it for other things. And next time we'll be talking about how to solve regression problems on computers. And we'll see you then.